Hi everybody, this is Cal with section 12.2, Vectors. We start at the bottom of page 815 with a little bit of terminology. If you've never seen vectors before, this is going to be pretty important for you to know. If you have seen vectors before, it should be review. This little bit goes on to the top of page 816. The really important idea here is kind of at the bottom of 815 and 816. The fact that vectors really consist of magnitude and direction, length and direction. And the same vector can start at different points and still be equal. So I can move a vector around and it's still the same vector. We're going to use this going forward. So we on 816 here talk about combining vectors. We start with vector sums. And we say that the sum of two vectors is what happens if I take the initial point of one and stick it at the terminal point of the next, and then just take kind of the resultant displacement. You can see it in figure 2 on the left. This is already making use of the idea that I can move vectors around. If you look at figure 5 and then figure 6, we have these two vectors A and B, and in order to add them, I move B so that it starts where A ends. So anyway, read this blurb and do read example 1 and go on to, so those cover vector addition. And then on the top of 817, we talk about what's called scalar multiplication. Now, your book says at the top of 817 that a scalar is what we're going to use to talk about real numbers to distinguish them from vectors. It's not really to distinguish them from vectors. It's because when you multiply a real number by a vector, it scales the length of that vector without changing its direction, as you can see in the definition of scalar multiplication. So vector addition and scalar multiplication are two very, very, they're basic ways to combine vectors. You'll notice that we have not yet defined a way to multiply two vectors by each other. That'll be in the next couple of sections. Your book also talks about what it means for two vectors to be parallel, what it means for one to be the negative of another, and how to talk about the difference of two vectors. Make sure you understand those. And example 2 is a good exercise to try for yourself. Then we get into the idea of components of vectors. This is when we use basically coordinate systems to talk about vectors. It's important to differentiate between a vector and the point at its terminal point. Whenever we talk about the coordinates of a vector, the components of a vector, we stick the initial point of that vector at the origin, and we say that the terminal point is going to be, the coordinates of that terminal point will be the components of the vector. And in order to differentiate vectors from points, we're going to use a little special notation here. We'll use these little kind of square braces for the components of the vectors. You'll also note that we'll always refer to vectors in boldface or with a little arrow hat, whereas scalars, real numbers, will just be normal typed letters. So start to get used to this notation here. So the blurb at the top here of 818 is pretty important. Do read that. Make sure you understand the terminology that they're using. Make sure you understand the difference between a point and a position vector for that point. Box 1 here is something we're going to use a lot, so make sure you understand that. The picture here goes pretty well, too. Example 3 kind of puts these ideas to use. Then we get into this idea of magnitude or length of a vector, how to find the length of a vector, and you're basically using the Pythagorean theorem on its components. This ought to make a certain amount of sense if you kind of draw out, maybe if we look at the previous page. We have this vector A sticking out from the origin. Of course its length is going to be root a1 squared plus a2 squared. And you can kind of see the same thing happening with a three-dimensional vector as well. Then we talk about how to add and scale vectors algebraically. You have the box at the top of 819, and example 4 gives a couple of examples of that sort of thing, finding length and so on. Make sure you work through example 4 and understand what it's doing. Then we get into a little bit more notation in the middle here, and then we get into properties of vectors, algebraic properties, how they work together. And they have all the properties that you would expect them to have. So read through these and make sure you understand them. Then in the middle of 820, we get into something that will be new for a lot of people. We have 3 vectors that we're going to define. They're I, J, and K. And these are just fixed vectors. I is always 1, 0, 0. J is always 0, 1, 0. K is always 0, 0, 1. These are fixed special vectors the same way that E is always 2.71828, whatever it is. Or pi is 3.14159, I don't remember. These 3 vectors, I, J, and K, are called the standard basis vectors, and you can kind of take them as a sort of notation. We will often refer to vectors in terms of I, J, and K, and you can kind of see here, midway between boxes 2 and 3, we have an example of 2 different notations for the same vector. One is using brackets, the other is using I, J, and K, and these just mean the same thing. Example 5 gives you a little bit more of an in-depth look. Then we get into the idea of a unit vector. A unit vector is a vector with length 1. You do need to know how to find a unit vector in the direction of a given vector, so make sure you understand what box 4 is saying. Example 6 gives an example where you're finding a unit vector in the direction of a given vector. Finally, at the end of the section here, we have an applications bit. Do read this little blurb and example 7 really carefully. You may be expected to do things like example 7. And that goes on to the next page. See if you can figure out what they're doing there. It's a drawing and a little bit of trig, and the key drawings here are in figure 19 and 20. And that does it for section 12.2.